So Milton will talk about full 3D nonlinear dynamics of charge and magnetized boson star. So yes.
Thank you, the organizer, for the invitation, and let me talk about my work. As you know, Milton is a really popular name in Brazil, so somehow I feel this link with Brazil. Okay, so this is a work in collaboration with Victor Jaramillo, Dario Núñez, and Miguel Silao, and you can find the details of this work in this paper that we recently posted, I do believe, a week ago. So if you recall the talk by Yuli today, he was talking about standard Newton boson stars, and now I'm going to do a little bit complicate more the system. And what I'm going to do is to put either charge or magnetic fields in the boson stars. So before I continue to talk about boson stars, just let me start about this stuff that is a really hot topic right now: multi-messenger astronomy and strong gravity. And as you know, uh, back in the early, I don't know, 2000 or something like that, we have observed black holes using electromagnetic radiation. And these are these little dots, reddish points that you see here. We have seen black holes with masses between around, I will say, let's say 5 solar masses to 20 solar masses. And also we have seen Newton stars with masses between around 1 to 2 solar masses. And once again, this is electromagnetic radiation. But now that we have gravitational waves, we have observed a new population of black holes, are these new blue points that you see here with masses between 20 and 200 solar masses. We also have observed, and it is important to mention that this object that appear here has been classified as black hole binaries. And the reason why they are classified as black hole binaries is because the mass. Okay, because we don't observe any object, or we don't know exactly what kind of object can has a mass larger than 20 solar masses, and we say, okay, this is a black hole. But this is important to mention that it can be another kind of things. And of course, we have observed binary neutron star mergers, and are these orange points that appear here. But because the sensibility of the detectors is not good enough, we don't know exactly what is the remnant. And this is why, well, maybe you cannot see it, but we have the remnant that we don't know if it is a black hole or a neutron star. This is why you see blue and orange there. All right, but important thing of this observation is this one. This is GW17OA17, and we believe that the remnant looks like this one that appears here, where we have 2 Newton stars with some magnetic field that extend from the interior to the exterior. This is somehow the pulsar-like or the magnetic field that you observe in pulsars. And this only observation allows to do a lot of physics. And this is what I'm going to try to summarize here. So we have done a bunch of physics using this observation. So for example, with Newton star properties, just using gravitational waves combined with electromagnetic signal, we have constrained the equation of state, and we know, for example, what is the maximum mass that a spherical Newton star can have. We have linked for the very first time from observations short gamma ray bursts with binary neutron star mergers. Now we have a better idea how we can form heavy elements heavier than gold. This is through nucleosynthesis. So what is happening is when we have the merger of the Newton star, they produce a lot of ejection of neutron-rich material, and that forms these heavy elements. Now, from just the gravitational point of view, you can use gravitational waves, and we know that GR predicts that we have two polarization, the standard one that are plus and cross. But there are another theories beyond GR that predict, for example, this brief mode. And if you detect that, then you can say GR is not complete. If you don't detect, then you can say you can rule out that theory. Another thing that you can say is that using gravitational waves and electromagnetic signatures, you can have a completely different measure of the Hubble constant that we haven't before. Now, fundamental physics, because we have the merger of the Newton star, then the remnant gets really, really hot, around 50 MeVs or even larger, that produce a lot of neutrinos, and then you can study the properties of neutrinos under extreme conditions. Also, because you have the merger of the neutron star, then you can study, for example, what happens when you have phase transitions there. Okay, so as you can see, we can infer a lot of physics using just that simple observation, that is gravitational waves, and that is really important, is electromagnetic signatures. Now let me go back to before, and when I was talking about compact binary mergers, as these objects that are here classified as black hole binaries. But now there is this paper from people from Aveiro, Carlos, and people from Valencia, saying that maybe one of these observations, in particular GW 190521, it is not a black hole, but is the merger of protostars. So that opened a new window, saying that maybe what we are seeing, it is not what we believe we are seeing. This is essentially what Gabriel was told us on Monday, and what Uli was telling us today, that maybe we are seeing more objects, different objects that we really know. But there is another question, is what happened why we don't believe that there are more objects more complex, with more complexity, like boson stars with magnetic fields. So what's going to be the final stage of these objects? So back in 2022, Dario and Victor produced initial data of magnetized boson stars, and in here I'm just presenting on the left isocontours of the field of the scalar field. This is the scalar field, essentially a boson star. And in here on the right, we have a pure poloidal magnetic field. So essentially what we have is a magnetized boson star. If you recall what I was showing yesterday, a few slides before, about GW 17017, what we believe, this is essentially what we have here. We have a star, and we have magnetic field that extend from the interior that go all the way to the exterior. So now the question that I want to address is, can these simulations, or can these objects explain some of the multi-measure observations? And I know, I'm pretty sure that someone is screaming already that maybe this is not the case, because the masses are not compatible with neutron stars. If you have a boson star, you cannot have similar properties with neutron stars. But maybe if you have a specific parameter, maybe you can explain, using the merger of these objects, some of the observations that we have seen. Now, if you recall what Claudio was saying, in order to study the merger of these objects, the first thing that you need to do is study the stability. What are the stability properties of these objects? And this is what I'm gonna do now. I just gonna study what are the properties of these stars. So for that, now thanks to Uli and Carlos, and many people are already introduced just a single star. The only thing that I'm going to do is to, instead to have just this action over here, I'm going to couple with the Maxwell tensor, the one that appeared here. And the covariant derivative, now I'm going to change it to include this vector potential over here through this constant Q that is related with the charge. Essentially, if you just, you will obtain the Einstein-Maxwell-Klein-Gordon system. I'm not going to go through the details. You once again have an answer for the scalar field, where omega is the angular frequency of the scalar field, and you have m, where m is this azimuthal parameter, integer parameter. Now I don't know what to do. Anyway, but now that you have the action, you can compute the equation of motion, and at the end of the day, what you ended up is with some equations, and you can compute the initial data of these configurations. And if I will show you what we have done.
The lesson is, don't try to do what you don't know how to do.
All right, I think that's fixed. So once again, you just get the initial data for these configurations, and when you don't have charge, So essentially what I'm going to do is I'm going to start with a single complex scalar field that is coupled with the Maxwell part using the distance that appear here, and you can compute the initial data. That's quite simple. So for standard boson stars is this curve that appear here. Nothing complicated. This is something that Uli already showed us today. But now when you increase the charge, this Q that appear here that is somehow related with the charge that you see, you obtain in the spherical case this curve that appear here. So what I'm showing is that when you increase, and this is for some specific value of this charge, you can compute exactly what is the charge, but essentially let's call it a charge. So when you increase the charge, what is happening, this is the mass of the system versus the angular frequency in units of mu. And as you can see, as you increase the value of the charge, you go from this curve to this one up here. So essentially, charge increase the mass of the system. This is for m equals 0, that means spherical case. But when you have axisymmetric stars, then you have this curve. This one is the standard one that we already know, but when you put more charge, then the mass starts to increase. All right, so now we have the theory, we have the initial data, we have a spherical star with charge, either this one that appears here that is spherical or this one that is axisymmetric. Now we need to study the stability properties, meaning that we are going to evolve and see what we ended up with these stars. So when people are talking about evolution, in general, we are talking about the Einstein toolkit, and I know that it's a jungle. I mean, Einstein toolkit is a huge, huge code where you have many thorns, you have many formulations, for example, the BSSN, the CC4 formulation, the C4C formulation. You have different thorns to do the evolution. You have many equation of motion for the shift. And essentially, what I just want to summarize is what we have been using. So we have the BSSN formulation, standard one. We don't expect that changing the formulation, for example, the one that Uli is using, the Z4 formulation, we are going to see any difference. The reason is because we don't have shocks when we have boson stars, so BSSN is good enough. We are using the standard puncture case condition, meaning 1 plus log for the labs and gamma driver for the shift. And there is an important thing that is in reddish here, is that when we try to evolve these stars using charge, they were really unstable if we use the standard 5th order Kreiz-Oelinger dissipations. We found that it's important to use a variable strength for every single refinement level that you are using. This is something that it has been proposed already by Bosola and Pascalidis back in 2022. And essentially what is happening is this system has to satisfy a kind of current condition. Anyway, but this is just a summary of how we do the evolutions. So now the first thing that we do is we take the spherical boson star with charge and we evolve the system. And what we found is that the system, this configuration, no matter what is the charge that we put, the charge goes from 1 to 2.5 in some units. This simulation is stable. This is the minimum value of the labs divided by the minimum value of the labs at t equals 0. Essentially one quantity that tells us how the system is evolving. So we see that the system is pretty stable, and we did just a zoom in just to show you what is the behavior. Essentially, because we're evolving this star, the star is oscillating because we have numerical perturbation, and the star is just oscillating as a sinusoidal function. Nothing unexpected. We already know that these stars are pretty stable. Now, what happened when we evolve the axisymmetric stars? And this is already when we don't have charge, we already know what is the behavior. What is happening is these stars are unstable. What is happening, these stars are unstable to m equal 1 mode, essentially what we call a bar mode instability. The stars are like this, and then they start to have this bar instability. They separate in two kind of stars. These stars emit gravitational waves, this little bubble of stars or scalar field, and then they merge and collapse to a black hole. Now the question is, what we will expect when we have charged axisymmetric stars, and what we discover is actually that the stars are more unstable. So essentially it's happening the same. You can see essentially the star have this m equal 2 mode instability. They break into pieces. These two pieces in spiral to each other, or they're in spiraling, and then they merge and collapse to a black hole. But if you see the time at which the instability appears, this is around 1200. In here appear in 1300, and this is for a small charge. So we just conclude that this configuration cannot be progenitor of current gravitational wave and electromagnetic observation. Essentially, why? Because this is unlikely that these stars exist. All right. So now, what happens if instead to have just charged stars, we have only magnetized stars? And the idea is here, when you have neutron stars, you magnetize the neutron star. Is what you are doing essentially is you add magnetic pressure. Because you are increasing the pressure, you are contributing, or you are putting more pressure against collapse. So you will expect that this configuration will be more stable. So essentially what we do is we superpose two boson stars in axisymmetric with charge plus Q1 and the other minus Q. And essentially the total charge of the configuration is 0, but that configuration produces a magnetic field. And essentially the only change that we have compared with the previous one is that we add another scalar field. And we repeat exactly the same recipe that we have done in previous one. So you have the scalar field, you assume that you have a guest. For example, for the scalar field that we call closed, it has omega t minus m phi, and for the other one is with positive m phi. You once again build the initial data, and what we discover is, in the past, I told you that when we increase the charge, the mass increases, but in here, this is once again the mass versus omega, the frequency of the scalar field, it reduces. So this guy is when we have 0, this is the axisymmetric star, and when you increase the charge, that is essentially increasing the strength of the magnetic field, it goes down. So the larger the magnetic field, the smaller the mass of the system. This is what we have here. All right. So now, what's going to be the outcome of this, the stability property of these stars? And turns out that it's basically the same. It is unstable to an m equal 2 mode. It separates or breaks into pieces, and then they merge once again and collapse to a black hole. Now, what's happening to the magnetic field? The magnetic field, when the instability appears, is like here. This is, I'm just plotting the strength of the magnetic field, and you can see that it looks like colloidal bit field. Then it contracts a little bit, and when these two objects merge and collapse to a black hole, a lot of the magnetic field is ejected. So at the end of what we ended up is just with a single black hole, and there is no magnetic field surrounding the system. So once again, these configurations cannot be progenitor of the observations. And now what we do, because we really know, what we really want is to have stable stars that can explain some of the observations. So we talked to Nico, in particular, Nicolas in Valencia, and he suggests to include this self-interaction. And with self-interaction, we discover actually you can repeat exactly the same game that we played before. And this is the new initial data. This is when you have a lambda equal 10 to the third mu square, but no charge. This is the one that we have here. And when you have a charge of 20, meaning a lot of magnetic field if you want, then we reduce the mass of the system goes to here. We evolve the system. This is what I'm having here. This is the mass versus time. And what you see that all the configurations are stable. So these configurations may be viable candidates to explain some of the observation if we can merge these objects. So just to finish, let me give you some takeaway message. So numerical relativity plays a crucial role linking various signals that we have observed. But the community, in particular the community of gravitational wave, they're always assuming, and this is a bias, I think, that we have classical compact objects. And by classical, I mean black holes and neutron stars. They don't allow more compact objects, which is weird. But now maybe there are new multi-messenger sources like these magnetized or charged boson stars. Now, in order to really see or to study what is the role of these objects, of these new compact objects as a viable sources of multi-messenger astronomy, we have to perform binary neutron star mergers, extract the gravitational waves, extract the electromagnetic signature, and compare with observations. And in here, I just take questions. Thank you.
Thank you, Milton. So please.
My question is about the stabilization with the lambda term.
Yeah,
Does that also hold for without electric charge?
Yes.
That's cool. So the interaction term actually might make some of the the spinning boson stars stable that we have so far regarded as
essentially
unstable.
this guy, what he's doing is adding kind of pressure. So this is why it stabilizes the system.
Yeah, what it does, it steepens the potential grows much faster.
Exactly.
So that means it's much harder to get strong concentrations of scalar field, and that's effectively a pressure.
Exactly, yes.
Cool, very nice, thank you.
Before asking the other questions, I have one more or less on the same topic. So, if you include self-interactions, would you also include charge or?
No, this is independent. So, for example, when you have charge equals 0, that is this case, this configuration that we have here, you have this family of solutions. But if you use Q equal 20, which is huge, you have this family. So, it is in the charge and the lambda, that is the self-interaction constant, are completely independent.
Okay, but the stable ones is also with charge, provided that you have the self-interaction.
All these configurations with charge, they're actually not charged because the total charge of the system is 0, but with a huge magnetic field, all of these are these configurations that appear here. Those are stable.
Okay. Are there more questions? Yes?
Thank you for your talk. I hope that you haven't mentioned this and I'm not asking something redundant, but when you had the case of the charged boson star, it would split into two, right?
Yep.
And then it would merge again in a way.
Yeah,
right?
this is basically what is happening. But yeah, basically.
And that, what's the final product? Is it a boson
So
star with charge?
No, it merged and eventually the system collapses to a black hole.
Okay, so
actually in all these configurations that are unstable, we didn't find anything. The only thing that was happening is they merge, they separate into pieces, they merge, and they always collapse to a black hole. We didn't see any dispersion of the.
Okay, and if you increase the charge even further, would that be enough to actually withstand both stars apart?
No, we really see. We start with this configuration has I don't recall exactly the charge, but we try to increase the charge to see if the charge can be stable. And what is happening is this time where the instability appeared was shorter and shorter and shorter. Was shorter and shorter.
Okay.
So
thank you.
no.
Thank you.
Other questions? No? Then let's thank Milton again.